And what I would like to do now is basically play with a bunch of different examples of abstract vector spaces to start building up a feel for them. And I'm going to do examples of finite ones. So the first abstract vector space I'd like to deal with is the set of functions that are linear. So ask yourself, are linear functions, the set of all linear functions where a and b are, let's just say, real numbers for now. You can do it for complex numbers, but let's assume they're real. A and b are all real numbers. Are these a vector space? I want you to talk to your neighbor about that for a moment. You have to decide, does it meet our four criteria? So just take a minute and ask yourself, does it meet our 4 criteria? Any thoughts? Does it meet our 4 criteria? How? Well, how would you define addition?
You add more additions to have like terms of x.
You add the powers of x and keep them grouped, right? So this is a case of normal addition in a sense where x stays a variable, and we know how to add that. So normal addition is what I would call it. And then everything else pretty much follows once you have normal addition, right? Do we have a 0 vector? What is it? 0. What's multiplication by a scalar? Just normal distributing the multiplication. So normal multiplication. And what's our negative? Well, there's no y here. Minus a and minus b, right? Just take negative f of x with our normal multiplication, and we've got everything. Now, where would you have to be worried? You know, I might, for instance, say linear functions where the coefficients are odd numbers. Now, does that work? No, because it's very hard to keep the coefficients odd, right? If I add, say, 3x and 3x, what do I get? 6x, is the coefficient odd? No, so it doesn't stay in the vector space. So a lot of times to prove it's not a vector, all you have to do is find one counterexample. Right? Now I might redefine addition, right, where the addition of odd numbers stays odd. That would be tricky, but you could imagine doing it. So that would be a different case. Now, what is the dimension of this vector space? Yes, it's 2. Why is it 2?
1 and x would make up everything.
Basically, if you think of the vector 1 and you think of the vector x, are they linearly independent? Yes, why? This is important. How did we define addition?
Add the like terms.
Yeah, we can't add these to get 0, right? We need to multiply them by 0 to get 0. Now, can I take any other thing, any other combination of 1 and x, and put it over here with 1 and x, and have the same situation, or will I always be able to get 0 now? Right? So if I take, let me put it, if I take the 3 vectors, 1, x, and a plus bx, is there some way that I can add these together so that I get 0 without using zeros as the coefficients?
Yes.
What do I do?
A and b.
Well, not a and b. Negative a and negative b, and I'm done. So any vector I add to these two becomes linearly dependent. So this is the maximum number of vectors. And that's what I'm saying. This is how we This is a proof, at least good enough for us physicists. And that would actually probably be good enough for mathematicians. But just to show how it works, using the Wronskian, right? If I wanted to look at 1x and a plus bx, those are my three functions. I'm trying to ask if they're linearly independent. What's the derivative of 1?
0.
And the derivative of 0?
0.
And what's the derivative of x?
1.
Derivative of 1?
0.
Derivative of a plus bx? Derivative of b? And what's that determinant?
0.
0. So these are linearly dependent because the determinant of the Wronskian is 0. Whereas notice the 1 in x, this little piece right here, what's the determinant of that 2 by 2 matrix? 1. So they are linearly independent because the determinant's not 0.
Is the Wronskian being 0 sufficient to prove that it is linearly?
Yes.
Is the Wronskian not being 0 sufficient to prove that?
They are linearly independent, yes.
Oh, okay, awesome.
Yeah, that's all you have to do. So this was dimension 2. Now what I'd like you to do is very quickly, with your neighbor, consider the set of all 2 by 2 matrices. We'll again stick with real numbers, though there's nothing wrong about doing complex numbers. Is this a vector space? And if so, what is its dimension? So take 2 minutes and try and do that real quickly. And again, feel free to chat with someone about it. What do we decide? Yes, no, maybe?
Yes.
Yes. So real quickly, what can we do? How do we add?
Just by adding.
Matrix addition. That's adding each component, right? That's the definition of matrix addition. So what's the 0 vector?
All zeros.
All zeros. What's the negative?
The inverse.
Everything having negatives. So the only real trick is what's multiplying by a scalar?
Multiplying everything.
Multiply every number by a scalar. That's the one that makes the most sense. So if I multiply this by 2, I get 2a, 2b, 2c, 2d. So now the real trick, what's the dimension? Why is it 4?
1, 0, 0, 0, 0, 1, 0, 0, and then so on.
So these are all clearly linearly independent. That's just obvious by construction in our definition of addition. And obviously, again, as with our functions, this is a case where it's obvious. If I add any other matrix to this, it's not going to be linearly independent anymore. So notice something we've done. What do we usually use matrices for? Not to represent vectors, to represent what? Well, we did for linear equations, but what, of my list of 4 things in that little summary of the abstract stuff, matrices were a representation of what? Linear transformations. Here, we're looking at the set of matrices as our objects. So what dimensional matrix would we need to represent a linear transformation on this set of vectors? Think about that question carefully. Well, what dimension is this?
4.
So if I was going to make them as column vectors, what column vectors would I use? I would do this. Remember, the representing the vector, right? These are not a representation of the vector. These are the vectors themselves. These are the abstract objects. The column vectors are the representation. So now how would I represent a linear transformation? By what size matrix? 4 by 4. So now a 4 by 4 matrix would represent an operation or linear transformation on this vector space.
So whatever the dimensions of the...
So whatever the dimensions are, when you go to a representation, that's what your matrix becomes, that by that. So matrices that represent linear transformations on my linear functions are what? Size. So for my linear functions, if I was to make a linear transformation of my linear functions, what dimension would that matrix be? 2 by 2. So these two examples are, I think, very important for getting down what we mean by abstract vector spaces versus the representation of the abstract vector space. And now the last little piece is, it's not necessary for the definition, but let's suppose we want to add the scalar product. Let's immediately point out a problem, right? If I have a linear function f of x and I multiply it times g of x, what do I get out? Real quickly, this is easy multiplication.
AC plus B plus dx.
AC plus B plus D x plus...
B dx.
Is this either a scalar or a vector? No. So normal multiplication gives me something that's unrelated to anything I've been talking about. It gives me a quadratic. So that cannot be the dot product. So f of x times g of x cannot equal fg. Likewise, if I take two matrices and I multiply them, what do I get?
Another matrix.
Another matrix, not a scalar. So one of the big ideas that we will develop in the next section is how we can go about defining scalar products. Remember, for geometric cases, we had a natural definition of AB. It was the magnitudes times cosine theta, because these were things we could measure. What we're going to find is for these abstract spaces, there may or may not be a natural definition. So what we might take is that the natural basis we declare to be of unit length and orthogonal. So we would declare these matrices to be unit length and orthogonal and write them this way, and that defines the dot product. We would declare 1 and x to be of unit length and orthogonal, and that would define the dot product. So we'll see that in the next example that we're going to do tomorrow. But I just wanted to prepare you for that. But the linear vector space is pretty easy to define and may or may not have a natural definition of the dot product. Geometric vectors have a natural definition of the dot product. Not all vector spaces do, so we impose it. And so you might say, oh, where did that come from? Or can you prove that? And I can't. We just chose that at times. So that's something else to be aware of.